Let's now take a look at this review problem. If k is greater than or equal to 0, prove that 11 is a factor of 10 to the 2k minus 1. This can be done either with or without induction, and we will ultimately use this to prove the rule for checking a number is divisible by 11. To do this, what we're going to do is the first part. We have the first lemma, so the proof of the lemma goes as follows. So proof of lemma number 1. There are actually three ways of doing this. We'll go from least formal to most formal. The least formal way is to note this, that 10 to the 2k minus 1, if I take 10 to any power and subtract 1, what I get is a string of 9s. A number, when you write it in base 10, is a string of 9s. And furthermore, because it's 2k up here, it's going to be an even number of 9s. A number like 0, or, well, 0 is the easy case, or 99, or 9,999, or 999,999. A number that has an even number of 9s in its base 10 representation. So it can't be 999, which only has 3 9s in it. Okay, now this you can factor an 11 out. The first 99 is 9, then it would be 09, and 09, 09. If you multiply this number by 11, you get a string of 9s like this, actually a string of 99s like this. And so 11 is a factor. So that's the first informal proof. The second proof, which actually does hold water, is if you write 10 to the 2k minus 1. That's the same thing as 10 to the 2k minus 1 to the 2k. So that's equal to 100 to the k minus 1 to the k, because 10 to the 2k is equal to 10 squared to the k. And so I can factor this out as 100 minus 1 times 100 to the k minus 1 plus 100 to the k minus 2 times 1 plus 100 plus 1. That's using a rule for factoring a to the k minus b to the k. 100 minus 1, of course, is 99, which is 11 times 9 times 100 to the k minus 1 plus 100 plus 1. And so we see that 11 is a factor of 10 to the 2k minus 1. And you should convince yourself that this final step in green matches the final step in red up here. A more formal way would be by induction. So the last proof is by induction. So the k equals 0 step. 10 to the 2k minus 1 is equal to 10 to the 0 minus 1, which equals 0, and 0 is a multiple of 11. In fact, 0 is a multiple of anything. Next step, we do the inductive step, or inductive hypothesis, so assume that. Uh, 10 to the 2k minus 1 can be written as 11 times something. So 11 times, say, little q, where q is an integer. K plus 1. 10 to the 2k, and I replace the k by k plus 1 minus 1. So that's 10 to the 2k plus 2 minus 1. Okay, so let's add and subtract 10 to the 2k to this. Okay, so I've not changed the number because I've added and subtracted the same number. 10 to the 2k plus 2 minus 10 to the 2k. I can factor 10 to the 2k out of the first two terms, leaving 10 squared minus 1. And for the last two terms, 10 to the 2k minus 1, by induction hypothesis, that's equal to 11 times q. Okay, 10 to the second minus 1, that's 99. So that's going to be 99 times 10 to the 2k plus 11 times q. And so I can factor out an 11, 9 times 10 to the 2k plus little q. So that's going to be equal to 11 times some other integer, big Q. And that's the end of the proof. So the first way is kind of the most intuitive way. The one in green is perfectly acceptable, except for the case where k is equal to 0. And the case in blue is the more formal statement. So that's the first lemma. The second lemma prove that 11 divides 10 to the 2k plus 1 minus 10. So that's fairly straightforward. So proof of lemma 2. Um, 10 to the 2k plus 1 minus 10 equals 10 times 10 to the 2k minus 1, just factoring a 10 out. So I factor out 10 to the first. 10 times 10 to the 2k is 10 to the 2k plus 1. And of course, 10 times negative 1 is negative 10. And that's equal to 10 times 11 times something. And therefore, 11 is a factor of 10 to the 2k plus 1 minus 10. So that's the end of the proof for lemma number 2. Now, before we state and prove the rule for checking if a number is divisible by 11, we actually have an intermediate step, which I didn't ask you to do in the review, but this will be very helpful later. Lemma 3. 11 divides 10 to the 2k plus 1 plus 1. Proof. This, I hope, is straightforward. 10 to the 2k plus 1 plus 1. That's the same thing as 10 to the 2k plus 1 minus 10 plus 11. Now the second lemma, we just got done saying that the first two terms is a multiple of 11 plus an additional 11, and so that's going to be 11 times something. So that's the end of that proof. Okay, let's combine these. Okay, lemma 4 goes like this. (11) is always a factor of 10 to the k minus negative 1 to the k. Proof. Well, there are two cases. If k is even, then I can write k as, say, 2 times j. Then 10 to the 2j minus negative 1 to the 2j equals 10 to the 2j minus, well, let's see, negative 1 to the 2 is going to be 1 to the jth power. So 10 to the 2j minus 1. And we already know by the first rule that if I have 10 to 2 times an integer minus 1, That's equal to 11 times something. That's the first case. Second case. If k is equal to 2j plus 1, it's odd. Then 10 to the 2j plus 1 minus negative 1 to the 2j plus 1. Okay, you should convince yourself that the second term is the same thing as plus negative 1 to the 2j. Just if I peel off one of the negative ones out of the exponent, then if I multiply this whole thing by negative 1, that cancels out and gives me a plus. Then as before, negative 1 to the 2j plus 1 is plus 1. So negative 10 to the 2j plus 1 plus 1. And we just got done saying that 10 to an odd power plus 1, that's equal to 11 times something. Okay, so we have this very important lemma, which I'm going to state up here. So let me copy and paste this so we can use this later. That 11 always divides 10 to the k minus negative 1 to the kth power. Now this can be proved directly by induction. I did it on this way on purpose to make it kind of appear less unusual. I think it works it comes out a little better with positive numbers, but you might want to check on your own to prove this statement in purple up here directly by induction. Okay, so finally we are now in position to state and prove the rule for checking that a number is divisible by 11. And the rule goes as follows. Theorem. Let n be equal to a sub k minus 1 times 10 to the k minus 1 plus a sub 2 times 10 squared plus a sub 1 times 10 plus a sub 0. And I should write out b, the base 10 representation, of n. Then 11 divides n if and only if 11 divides a sub 0 minus a sub 1 plus a sub 2, and continue on. The even ones are plus, the odd ones are minus, and so I stop with negative 1 to the k minus 1 times a sub k minus 1. Proof. Well, the proof will be fairly straightforward using the lemma in purple that we wrote up top here. 11 divides n if and only if 11 divides a sub 0 plus 10 a sub 1 plus 10 squared a sub 2 plus 10 to the k minus 1 times a sub k minus 1. So that's the definition of n, just simply reversing the terms where a sub 0 is now first and the highest power of 10 is last. So that's a multiple of 10 if and only if I were to subtract a multiple of n, and it's still a multiple of n. So let me copy this directly. Minus, well, according to my rule here, if I take 10 to the first minus negative 1 to the first times a sub 1. That is clearly a multiple of 11. In fact, it is 11. Minus 10 squared minus negative 1 squared times a sub 2. That's a multiple of 11. In fact, it's 99. Minus, and I continue to subtract off, 10 to the k minus 1 minus negative 1 to the k minus 1 times a sub k minus 1. And that's basically the line I have here in purple, just replacing k by k minus 1. Okay, so I know that all of these terms here are multiples of 11, and so if this thing that I'm circling is a multiple of 11, then if I subtract off all of these multiples of 11, then this big thing must also still be a multiple of 11, and vice versa. So when I do the subtraction, a sub 0 is by itself. Here I have 10a sub 1 minus 10a sub 1, those cancel. Then I have minus, 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 so minus a sub 1. Then 10 squared a sub 2 minus 10 squared a sub 2, those cancel. Then minus, minus cancels, leaving me plus a sub 2. And they continue to alternate plus and minus, stopping on negative 1 to the k minus 1 times a sub k minus 1. So the original number is a multiple of 11 if and only if I alternately subtract and add the digits, this new thing is also a multiple of 11. And so that's the end of the proof.